Hey everyone, in this video I'll be looking at this live Kaggle Competition Feedback-Prize English Language Learning, where I will be working with Deberta-v3-large V3 model, which is a pre-trained model and available in Hugging Face, to predict the English language essays written by students. And that is the very target of these live Kaggle competition. And remember, again, this is a live one. That means if you win this competition, you will win a prize money of $55,000. Anyway, so that about we have got three data sets here: train CSV, test CSV, and sample submission. The most important ones are these two: train and test. The training set comprising the full text of each essay identified by a unique text ID. The essays are also given a score for each of the 7 analytic measures above: cohesion, etc. These analytic measures comprises a target for the competition. And for the test CSV, for the test data, we have only given full text. Okay, so let's look at the train CSV first. It will make sense then. Okay, this is our train CSV, and one second. And what we got here is a unique ID for that kind of represent each student. And then I have a full text. And then the different heading under which this text is measured and the scores given. So one heading, for example, is cohesion, and this particular writing got a score of 3.5. Then syntax 3.5, vocabulary 3.0, and so on. I have got even more heading. Phraseology, grammar, and conversational, what is that? Conventions, okay. And so that's my train CSV, and in the test CSV, I have only got unique IDs in the text, and the job here is to look at this text and predict those other scores under those different headings. And what are those headings again? And these are the headings. And if you are interested of what exactly these headings means, the competition host has given a document here, Google Doc, where all the definitions of those headings are mentioned. For example, the cohesion represent a text organization consistently well controlled using a variety of effective linguistic features such as reference and transitional words and phrases to connect ideas across sentences and paragraphs, appropriate overlap of ideas. So very much these are the metric by which that text will be rated or scored under the cohesion heading. Then let's look at grammar. It's obviously command of grammar and usage with few or no errors. Then, for example, the syntax, flexible and effective use of a full range of syntactic structure, including simple, compound, and complex sentences. There may be rare, minor, and negligible errors in sentence formation. Okay, so that's how those heading means and the significance of those headings, and these are the various scores that these writings have obtained. So and that's what I'm looking at train CSV, and those scores will need to be predicted under the test CSV. That's the whole purpose. All right, with that, I am already inside my Kaggle kernel. The first cell, I'm just importing all the libraries, and specifically to mention that I'll be using Deberta-v3-large, and that's why I'm importing all these transformers and related modules. And also I'll be using PyTorch for this. And here also I'm importing some more libraries, and here in this next cell I'm just defining all the root directories or necessary directories. So my base directory is Kaggle working, then ds train path, which has a train CSV, ds test path, which has test CSV, sample submission path, which has sample submission. Now, save directory is where my model, some other models that I have used, pre-trained models, those are available. And also Deberta-v3-large offline path. That's where I am saving the Hugging Face model, because in this kernel I am not using internet. If you know that in Kaggle kernel you may switch on or switch off the internet uses. So if you are not using the internet, that means you need to save the model actually in a path, and that's where that's this path means. And when I'm running pwd, that means present working directory, that will just show Kaggle working. And here I'm just printing all the available data sets or models for this particular notebook. Remember, if you want to add a data set, you need to do it from inside the kernel. And for that, you just open up these right side menu, you go into your data, and here you click on add data, and there you can choose whatever models or other data you need to add. So in this case, I'm using some pre-trained model which are saved, and these are those models. So this one is obvious, Deberta-v3-large, which is Hugging Face Deberta-v3-large model. And then I'm also using another one, Deberta-v3-large. This is another pre-trained model that was used by many other Kagglers who have scored high in this competition. So I am also making use of this model, and this is a pre-trained one. You can just search by this name and you will get that. And the first one is obvious. This is the actual input data of this competition. And I will give a link of these two other models that I'm using in my notebook and in the source code. You will get that in the GitHub link down at the description section of the video. And otherwise, I'm obviously using the GPU because I need that. Okay, so yeah, so now when I'm printing the all my files that are available inside my working directory, that is Kaggle input, these are those files. Okay, and here you can see my train CSV, test CSV, submission, sample submission, and these others are the pre-trained models. And then also this Deberta-v3-large, this is also my pre-trained model. So with that, this is all the things that I need to work in this video, in this notebook indeed. And then this small class is a config class. So all I'm doing here is defining all the configurations for my model. So base directory, device, seed of 69, dataset path. I have quite a few dataset path here. And then tokenizer parameters, truncation 2, padding false, max length 512, model name, I'm using Microsoft Deberta-v3-large. Target columns are just the different column names that we need to predict. Learning rate 0.1, batch size 5, epoch 5, and folds 5. Okay. So that's my configuration, and I'll be using this configuration many times. And just a quick, just to see the data, as we already saw this in the actual CSV file, but here I'm just printing the head with as a data frame by reading it with pandas data frame, and this is the data set. So I have the text ID, which is unique. Then I have the actual text, full text column, then cohesion, syntax, vocabulary, phraseology, grammar, and convention, which are the different headings under which these texts are scored. And I'm supposed to predict these scores for the test data set. Now time to do some basic EDA here. First, I'm just going to do a heat map for checking the correlations. All right. Yeah. Kind of many of them are on the higher side of the correlation among them. Okay. Now I am going to make use of some plotting of histogram. So of the various target values, that is cohesion, syntax, vocabulary, etc. Trendy or full text. Discrete. Color discrete sequence. I need a particular color code, hex code. That's this. Plotly dark. Finally, I want to use color. I need the hex code, which is this. Histogram got an unexpected keyword argument title here. The spelling Title. Cool. So that's my Plotly histogram of full text string length. And we can see that the concentration is towards 2000 to 2200, something like that. Okay, now I want to do the same histogram for each of the target, that is each of the features in my data frame, which are, what are they? They are cohesion, syntax, vocabulary, I think phraseology, etc. So first define the colors for the 6 heading, 1, 2, 3, 4, 5, 6 here. So I can just put the, let me copy the column names. Original for the previous plot was, I think, box, yeah, and this one I want to use violin. Name GIG is not defined. Where is that? Cool. Now they just drew the histogram for all the 6 targets. So cohesion, syntax, vocabulary, phraseology, grammar, conventions. Okay, cool. And now pre-processing before starting the model configuration, etc. And during the pre-processing part, first I will have few util function to deal with the encoding error. So the first one is replace encoding with UTF-8. Error of type here, and that actually will give me so about this encoding and decoding, you can read further in the Python's codex page. This one, you can just go to library codex.html. That will give you more details about these various encoding methodologies, decoding methodologies, etc. So next I'm going to replace decoding with CPL1252. See. And then I need to now register the encoding and decoding error handlers for UTF-8 and CP1252. Codex.register error. So what was this name? Copy this whole thing. Similarly, and now I need to resolve the encoding problems and normalize the abnormal characters. So the last util function in this regard. Errors. Then I need to pause here, replace decoding with CP1252. Next here is replace decoding here. You need decode. All right, now the friend will be just read CSV train path. Similarly, I need to do for DF test and DF submission. DF train dot head. Yeah, yeah. So now I need to apply to these DF, actually to all the DF train test and SS, these Unicode resolving methods. So, and I need to apply these only for the text column. So first one is resolve encodings and normalize. What is that here? DF test. Config dot and now finally I am ready to define my tokenizer. What was the name that we defined? Yeah, Deberta-v3-large path. Run it. Okay, so this is our data frame. Now define a utility function named tokenize. Tokenizer, and then we'll get text. DFI. All the target columns from our original data frame. That will be my tokenized labels. So config dot that will be input IDs. Okay. And so now that my tokenize is ready, I need to do a little bit of things here to check the proper data set from pandas is obtained here. So from pandas. This df test has already been defined earlier. Let's quickly see. Df test, yeah. So df test is just pd.read csv of my ds test path. That looks good. So now, so that's what I'm reading here, and then ds will be. So this map function is coming, it will take the tokenize and also a couple of configuration like badged, description, etc. So tokenize badged equal to false. This map function is actually coming from Hugging Face because I'm reading a Hugging Face data set here. Or description equal to, yeah. And a quick word on this map function here, because this is a very useful function and will be used very often when you are working with Hugging Face dataset. So the primary purpose of map is to speed up processing function. It allows you to apply processing function to each example in a dataset independently or in batches. This function can even create new rows and columns. In this case, for example, this map function is applying the tokenize method that we just defined here on each row of our data frame. All right, with that, let's proceed with here. So after my dataset is defined and properly, this tokenize is properly applied to each rows, now I'm going to save to disk. And here, this is where it is going to be saved. Data.dataset. Based here. PKL. Dump pf test fp. Okay. Now at this moment, if you just want to see what this Hugging Face dataset for us looks like, just print this dataset. So as expected, this dataset is in a special type of structure. This is specific to Hugging Face dataset, and what I'm getting is a dict with features and number of rows. So for the features, I have full text ID, full text, cohesion, syntax, vocabulary, phraseology, all of them. And you can actually print only the keys. DS0 will give you the full text. So let's just print the keys. Yeah, so that's all the keys in the dataset. Text ID, full text, cohesion, syntax, vocabulary, phraseology, grammar, convention. Up to these we already know because these are our features in the original dataset, and then I am getting the specific things which are specific to Hugging Face, particular way it saves dataset. I have input IDs, token type IDs, attention mask, labels, and length. Okay. And next, before our modeling, the most important thing we have to do is to take care of pooling. And we are going to use mean pooling and max pooling here. So before understanding pooling, you need to understand what is the difference between token embedding and sentence embedding. So sentence embedding play a completely analogous role to token level embeddings, with the main difference being that, as the name suggests, that there is only one embedding for the entire sequence rather than one embedding per token. So the process of converting a sequence of embeddings into a sentence embedding is called pooling. So intuitively, this entails compressing the granular token level representations into a single fixed length representation that is supposed to reflect the meaning of the entire sentence. And that's the job of pooling. And this image fundamentally shows the architecture of the pooling mechanism. So essentially, sentence BERT adds a pooling operation to the output of BERT or Roberta model to create a fixed size sentence embedding. And a fixed size sentence embedding is the key to producing embeddings that can be used efficiently in downstream tasks such as inferring semantic textual similarity with cosine similarity scores. And the sentence BERT does this by a pooling strategy. The default pooling strategy of sentence BERT is mean pooling strategy. There's also another pooling strategy called max pooling. So now what's the difference between mean pooling and max pooling? So under the mean pooling, if we obtain a sentence representation by applying mean pooling to the representation of all the individual tokens, then essentially the sentence representation holds the meaning of all the words or all the tokens. But under max pooling, that is, if we obtain the sentence representation by applying max pooling strategy to the representation of all the tokens, then essentially the sentence representation holds the meaning of only the important words. Alright, that was about the theory of mean pooling. Now I'm going to code it, and for mean pooling there's some boilerplate code indeed available in the documentation of Hugging Face and also Tensorflow and few other packages. Basically, I'm going to extract the attention mask, unsqueeze it, and change the dimension or view the dimension with expand method, and then apply averaging to the sum of the embeddings. Let's just define that. And this code, this particular code, or rather this technique of calculating mean pooling, will be used in many projects in NLP wherever you are trying to do sentence embedding. This is here I'm using PyTorch, and that's why this is in that module here. So I can get all the methods from nn.module. Diff attention mask dot unsqueeze. Expand it to view it in a particular with a particular size, and that size will be last hidden state, that size, and then apply float. Now sum of all the embeddings will be last hidden state, multiply that with input mask expanded. Clamp it with torch.clamp between values of sum mask and finally my mean embedding will be sum embeddings divided by sum mask. That is all. And the next method that I'm going to, the class that I'm going to write is going to be the longer and the main class for our training, for our applying the Deberta pre-trained model on my data. But before proceeding further, quick word on this last hidden state here. What we see here that we are getting these, we are applying this expand on the last hidden state. And what is this last hidden state? So the BART model without any heads on top outputs two things: last hidden state and puller output. This last hidden state contains the hidden representation for each token in each sequence of the batch. So the size of this last hidden state is batch size by sequence length by hidden size. And this last hidden state is the sequence of the hidden states at the output of the last layer of the model. All right, now let's move on to our main class. Deberta-v3-large. What was the name? I think no, I need to pass a dict here. And that dict will be output, hidden state, hidden dropout probability, all these things here. Attention probes drop out, that's 0. Add pooling layer, false. Okay. Transformer. This is where I'm loading the Deberta-v3-large model. Again, I need to pause the path here. We have already defined this model config right here. So again, because this notebook in Kaggle I'm using without internet, and that's why I have to pass a local path to this Deberta model. And also for this config, I'm passing this local config.json file. But if I was connecting to internet, then I would not do this. I could get the config something like this. Sorry, not this one. I could get the config. 1 second. So actually, let me type that. In that case, it would be transformer model equal to and path would in that case would be the original path, whatever, like Microsoft Deberta. And for the config, I would just do config equal to self.model.config. Yeah, and this one will actually fetch the config.json file from the internet. That is from the original models hosted in Hugging Face. But here I do not have internet, so I am not using this line. Okay, so my model is defined. Next one is I need to define the layer norm. So I can make use of PyTorch nn.layer norm. Transformer model dot config. I need to get the hidden size. Multiply that by 2. Okay, this is important here. Note that I'm multiplying by 2 is because we will see in a second that we will be concatenating the mean and max pooling. So that's why I need to multiply the hidden size by 2 because I'm using both mean and max. And next is self.output. That's a linear layer. The first one will again take this whole thing. Actually, I can just copy. Self.transformer model.config.hidden size multiplied by 2. Yeah. And the next is my length of the target column. Target COLS. And this I'm getting from my original config, which has been defined right here. Target calls all the feature names in the data frame. Okay, that's output. Next one, I need to define hidden layer weights. That would be parameter. Oops, it's not there. torch.zeros. Model config layers, and that I need to view, change the view with -1, and the rest are all 1. 4-dimensional tensor it is. Okay, and next I need to define a dropout layer, and for that I'm going to use a module list. So drop out should be module list, and to that I will pass a list, which will be nn.dropout multiplied by I in range 5. So these nn.module list is just like Python list. It was designed to store any desired number of nn.modules, and normally it may be useful, for instance, if you want to design a neural network whose number of layers is passed as input. So why we use module list instead of normal Python list? And that's because if you use a plain Python list, the parameters won't be registered properly and you cannot pass them to your optimizer using model.parameters. And that's why you will see a lot of use of module list in a neural network architecture. Okay, so where I'm doing this here, 0.1 multiplied by I for I in range smooth L1 loss is what I'm using. Reduction method. Alright, with that, this initializer constructor function is done. Next, I need to define the all-important forward method. Output, let's name it output backbone. Transform model. Now extract the hidden states. And now I am going to do a min-max pooling over hidden layers and then concatenate with pooler. So tuple, and for the hidden states I need to do minus I minus 1 I in range len hidden states, and then minus 1. Need to define the dim as well, dimension across, dimension of 0. Hidden layer. Torch.sum, sum over the hidden states multiplied by layer weights. Hidden states. And now finally concatenate with pooler, that is concat the mean and max pooling. Output backbone. Out mean and out max. And similarly, backbone output backbone. Then from here, I'm going to take everything from the first dimension, 0 from the second dimension, and everything from the last dimension. Now, configure for multiple outputs. Dropouts. Self.output. Output backbone. Remember what was our output? That was a linear layer. This line right here. So logits in this case will just be equal to self.output. Else self.output. Okay, that's it. Now return logits. Okay. Now next, I need to just define two quick functions, which is train data loader and validation data loader. Upstream. Data loader, and also Okay, and now I need to define a helper function to differentiate the parameters that should receive weights decay. So basically now I have to take care of the optimization process with differential learning rate, etc. So define this method called get weight decay, keep it at 0.01 as the default value. Yes. And now I need to define a list where they are not subject to weight decay. So this list is this bias layer norm.bias and layer norm.weight. Finally, I should be able to define optimizer parameters. This will be a list of EARAs. Transformer. If not any, very important. If not any, then N for ND in no decay list. All right. And the learning rate is actually this one will be weight decay, WE. Okay. And the next one, I can actually copy this thing, then change few things. P4 np in self.transformer dot name parameters. And now it will be the opposite. If any nd in n for nd in no decay list, right? And in this case, the learning rate is encoder LR, weight decay is 0 and 0. Sorry, 0. Okay, and finally copy and paste again and change few things here. P4 NP. Okay, this one will be self dot named parameters. If okay, let me just change it here. Trans okay, and error is decoder error with decay is 0.1 0.01 indeed. And another function in this respect is to for the configuration of the optimizers. And now define a warm-up step. So the idea of warm-up steps is to use some warm-up steps to increase the learning rate gradually up to a certain point, and then only then use your normal learning rate decay afterwards. Warm up. I need to divide epoch steps by batch size. And here I'm going to use the function that we imported earlier, which is get polynomial decay schedule with warmup. This is one of the strategy to decay the schedule, to decay the learning rate from the PyTorch library. So you can definitely go and read about it, what it does. So basically this method, okay, we will discuss that later actually, because now let's complete it first. First one it takes is the optimizer. And power. Oops, sorry. Okay, that's my scheduler. Now my learning scheduler config. And finally, we return from this method a dict with config. All right. Okay, now coming back to this get polynomial decay schedule with warmup. So this creates a schedule with a learning rate that decreases as a polynomial decay from the initial learning rate set in the optimizer to end learning rate defined by the LR end after a warm-up period during which it increases linearly from 0 to the initial learning rate set in the optimizer. That's how it works. Okay, now we are done with that. Now I need to define a predict function for evaluation that will take data. Config that device. And what else? Zero. Val.reshape -1. Dot two. Eval in okay. Now output. Inputs. From there, I take input ideas. Inputs. False. Let's extend this tensor, prediction tensor, with outputs dot number. So basically what I did in this method is I'm looping through the batches, and for each batch I'm getting the inputs from the batch.items. Then from that inputs, I'm actually then passing that inputs to my model. And how I'm passing, because to the model I need to pass the inputs, then input IDs, and also the attention mask. So both of these input IDs and attention mask I'm getting from the inputs tensor. That, when passed to the model, produces my outputs. And then I am doing prediction.extend and then passing the outputs as a pure numpy after removing the gradient from it. And then so that was a single batch. Now after all the batches are done, I'm just doing a vertical stack of all these predictions to produce my final predictions, and that's what I'm returning from the function. Okay, now finally time to run these training and derive the predictions. Data. define a set of columns to keep this is where I'm removing some of the columns which are not in keep calls. Okay, and now test. I'm creating the data loader for feeding into the model with test.ds. This is where I'm using this collator that we defined right here. Okay, that's my test data loader, and now model. And I'm loading from the checkpoint. We already imported some of the pre-trained model and dataset, so that's what I'm going to use now. And that this was saved in the save d that we defined in the config, so I need to get it from there. Config dot save dir, and then comes Microsoft Deberta-v3-large. That's how the saved model was named. That is Deberta-v3-large underscore the fold number, and also .ckpt because it's a checkpoint. Okay, then train data loader will be none, and validation also none. Config equal to config. Okay, now finally my preds tensor. So here I'll be using the predict function. To that I'll pass the test data loader and the model. And look how we did the predict function. It will give me the prediction as the vertical stack of individual prediction from each of the batches. So from this prediction, now I need to run a little if condition. Fold. Oops. Parents plus equal to. Okay, and finally I can just delete some of the variables which I don't need. Model, test, data loader. Cool. And after this, so now this is my training and the final predictions from the model. And then I'm going to use these final preds, this variable in the next cell, to create my submission data frame. Because as you remember, in the test data set, there were only unique IDs and the text, and I'm supposed to predict all the columns. So that's what I'm going to do, and create my data frame for submission. SDS config.baseDiv. The base div and then data set. I text. Okay. Fine. Let's just print it to check the shape. And now my final submission data frame. So one columns just for the test IDs. Text ID. And now add another column with all the target column names and the scores for all those features or target columns. Config the target calls. That's it. My data frame should be ready now. Let's just check the head of this. So I'm back in the Kaggle kernel, and here my training code ran. So this is where the folds were running, and yeah, so after all my folds ran, I ran these code here to create my data frame, and this is the final data frame ready for submission. So after this, I just run these two CSV method on these from this data frame to create submission.csv, which I will submit to the Kaggle competition. And with this submission, I got a public score of 0.44 in the competition's public leaderboard, which is not too great because all the top scoring from all in the leaderboard was 0.43 or better. So, but remember, this was a very baseline submission. I did not do any data pre-processing that much, or any tricks or any feature engineering. It was just a direct application of Deberta model on these dataset to create a baseline submission. So, so on top of these, there are many ways to improve, many strategies to implement, but that's a subject of a totally different project. This exercise was purely to check what a baseline implementation of Deberta-v3-large could produce for this kind of competition. Alright, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.